I'm Adam, the co-founder and CTO of SkyMind. I created something called Deep Learning 4J, not targeted at data scientists, but production deployments. So written in Java, optimized in C++, optimized for Hadoop and Spark, and Android. So I'm here today to talk about anomaly detection and deep learning. So what I want to do is just give a brief overview. So basically what I want to do is just go over the use case of network intrusion itself. So like, what is it? Hacker, think about hackers, identity theft, all sorts of crazy stuff like that. Kind of just go over anomaly detection. So like, what is it? Why should you care about it? What are we doing today? And then, why deep learning for this? Because, when you think of deep learning, you think of computer vision, you hear about speech recognition. That's what's talked about in the news, right? But that's not actually that's not where the money is, turns out. It turns out not only can you do object recognition or speech recognition, but you can actually solve normal everyday problems that you actually get paid as a data scientist to do. Your company always has tabular data, right? Deep learning, turns out, is actually good for those kinds of problems. It's good at servicing problem. I'll get into this in a bit, but basically problem like behavior. It's good at finding patterns in behavior. So that's kind of what I want to talk about today. And then what I'll do is give kind of a high-level demo of just a solution that we built for deep learning. And what I want to do is just kind of go through not only an end-to-end workflow, but also what does this look like? What would this look like in a product? So this is the applications track. So there's not a lot of math. That being said, if you have math questions or anything about deep learning, my last presentation I gave was actually distributed deep reinforcement learning on Spark for network intrusion. So I've done some stuff out there that's on the level of DeepMind, but I also do everyday applications. So I'm more than glad to talk about any range of questions you may have. So starting out here, so network intrusion. So what is it exactly? Network intrusion is identifying hackers. So imagine right now, imagine the hotels or the Wi-Fi here is being compromised right now. Everybody's sniffing your traffic, right? And maybe the venue doesn't want that. So instead what they do is they want to detect that, and they want to shut that activity down, right? Like, so you have hackers on a corporate network. You have, just basically bad activity. So what would an intruder do on a network? What does intrusion mean exactly? So intrusion in this case means I'm in your network and I'm looking for sensitive information, right? I'm looking for things that could help me gain, give me financial gains. I'm here to steal from you, right? Like that's what network intrusion is. So that's what you're out here to do. So you're basically what you want to do with network intrusion detection is you want to detect this activity based on just raw time series. So click logs on your network. Think about a very simple way to think about this, like the kind of data you kind of analyze is logs, right? Like, so you go to google.com and your activity gets logged. So you ping the server and it gives you back a response. That gets logged, like that kind of activity. So central IT at your company is, they are watching. They are watching you. They're monitoring your activity. They're looking for certain kinds, like, how often are you on Facebook? That kind of stuff, right? That does exist, right? And so that kind of auditing technology is also used for detecting hackers in both internal and external networks. So what I want to talk about today is mainly oriented towards external, right? Like, because that's a more common problem, because basically the whole point of this is I want to expose a service to the internet, but I don't want my service to be compromised. How do I do that? Turns out you use network intrusion to do this. So what do we? So network intrusion itself, though, is actually a part of a broader class of problems called anomaly detection. So what I want to do is just go over some basic anomaly detection use cases, right? Like, so you have anomaly detection. You want to detect a rare pattern in data, right? Like, so what does it mean, a rare pattern? It could be online credit card fraud, right? You have, in this case, banks have online transactions. You're accessing your banking account from mobile or online, and you basically want to detect, somebody's stealing from me. Somebody's actually using my credit card for things I did not intend, right? So that's an anomaly. That guy who's stealing from you is an anomaly. So hackers on a network is also an anomaly. And then in this case, one use case I'll talk about in a bit is also SymBox fraud. The ability to actually fake activity on a network and actually leech off the carrier network. So a carrier network in this case is your phone. So when you call, you're on the carrier's network and you're using their infrastructure. So leeching off of that infrastructure is a problem for telcos. So this is a wide range of problems I like to categorize as finding the needle in the haystack. So finding the needle in the haystack it's commonly used in business as the needle is the target behavior I'm trying to identify. So that's anomaly detection itself. Depending on the vertical, in this case we primarily deal with financial services and telecom. But there's any number of verticals that this could be applicable to. And so anomaly detection is just part of a wide class of problems of finding the bad behavior, finding the thing that's costing you money. It could even be, in this case, broken hardware. How do you, I want to predict when servers are going to die, right? So that's preventative maintenance. So that's another form of kind of anomaly detection. So I just want to briefly go over one use case that isn't network intrusion, just so you can kind of find the similarities. So one use case that I can talk about publicly is France Orange. So they're the biggest telco in France, and basically one of the things we did for them was we actually based on raw carrier data from Africa and France, we were actually able to identify people using something called a SymBox, which takes calls from Wi-Fi and routes them onto the carrier network. So that costs Orange $3 billion annually. So you want to identify that activity and to shut it down. So one of the things we did with deep learning was without any labeled data, they didn't tell us anything. They just had rules. They didn't tell us anything. We were actually able to find new sources of fraud, of people leeching off these carrier networks. So what happens is we found more activity, and we're actually able to help them shut down these SymBoxes that take calls from Wi-Fi and route them onto the carrier network. We're actually able to shut them down. So that's SymBox fraud. So what are the similarities there? You're trying to find the target behavior, finding the hackers, finding the people leeching off your carrier network. It's bad activity. So in this case, what we analyzed was, you have web traffic, and then you have call logs, right? So a call, again, if you're on your phone and you take a call, right? And so what you're doing there is you're speaking, right? So you have various activity log, but you have who called, when, the location, right? So that's also a pattern over time you can recognize. So it's the same thing. So you have patterns over time you're trying to recognize. And in this case, the needle here, the needle in the haystack was the bad call, the fake calls, the people not paying. So you want to shut that activity down. And so network intrusion, also time series data, right? And what you want to do is you want to find the hackers on your network. So it's both the same kind of problem. It turns out deep learning with actually just minimal modification can be very suitable for various kinds of anomaly detection. And so the great thing about deep learning and machine learning is that you change the feature vector, but a lot of the applications and data pipelines can stay the same. And so in this case, deep learning is good at surfacing patterns and behavior. So what do I mean by, I've talked about behavior already, but let's think about where deep learning came from. Deep learning came from billions of dollars of ad tech R&D. So when we think of deep learning, what are the companies we think of? We think of Google, Facebook, Baidu, right? Those are all ad tech companies. Imagine that. Amazon, they're starting to do some deep learning now, and they're using it for logistics. They're using it for all sorts of crazy use cases, mainly recommendation engines. And so Amazon, for example, Amazon has used our software twice for actually improving their search and their targeted advertising on Amazon.com itself. So it's good for, again, it's just good at surfacing patterns and behavior. So it started in ad tech, where I want to profit off of I know what all you guys are doing, I know what you guys are clicking on, and I want to be able to recommend you an ad. I want to be able to recommend you a new product. I want you to buy something from me. So it turns out deep learning is actually very good at increasing revenue for these kinds of large-scale hyper-tech hyperscale ad tech companies, or in this case, e-commerce. So Netflix, for example, Netflix also uses deep learning for some of their internal recommendation engine stuff. So basically, anytime you want to surface new kinds of behavior, or you want to understand what is going on in this large blob of user activity, deep learning, it turns out, is a better way to do it. But when we think of deep learning, we think of object recognition. We think of how many faces are in the room right now. That's a cat. That's a dog. Speech. Speech to text. Siri. Siri uses deep learning, for example, right? Like a lot of kind of media analytics, raw data, raw binary data that's user generated, like person generated, is analyzed with deep learning today. But it turns out you can also use it for just plain time series data. With minimal preprocessing, you can actually come up with a feature vector that a neural net can use for identifying targeted patterns. And in this case, you can do both unsupervised, which is no labels, and supervised learning, traditional machine learning techniques, right alongside your normal, neural nets. And you turn out you can get better accuracy on certain kinds of problems. So what I want to do is just go through kind of an example walkthrough. One problem with typical deep learning talks is they have all this math, right? But what's the application? What does a complete product look like? No one thinks about the data pipeline, the actual product, all the way down to your mobile app. You using the app itself. What does this infrastructure look like? So what I want to kind of do is visualize what an actual product could look like and what an actual use case would be. And so what you're going to see from me here today is a big data analytics infrastructure, and a walk through that, and applying deep learning within that context, focused on network intrusion. And so what do we start with? So I mentioned earlier this idea of web logs, right? So a web log is your time series data, your activity. That data is going to come from tons of sources. If you think about it for a second, like how many clicks does Yahoo Japan get? They have terabytes of data that they go through. I mean, I don't know how many you guys use Yahoo Japan, but it's all over the place. Most of Japan is hitting their website, right? And so that generates lots of data, turns out. And so it turns out there's different ways to store that data as well. You have different kinds of databases. But at the end of the day, you usually want to have specialized data stores for these kinds of things. So what you end up with is several data sources. Different kinds of traffic get routed to different kinds of databases. And so you need to actually aggregate and combine that data. You need somewhere to store it, and you need a place to analyze it. So you have all these sources, and so you have a data source, and then finally, you get to then needing to aggregate that data. So now you have so for an example here, if you can't quite visualize this, imagine all these web logs as a stack of papers, and you need to sort through these papers, right? Like so what do? You have people coming to you, and they're dropping off things at your desk, and these papers are accumulating and accumulating and accumulating. So that's kind of your raw data source. So you can think of this as bureaucracy. That's a great example. So bureaucracy, and you have papers piling up. So now you need something to analyze it, right? So you have a stream now. So what does that stream do? That stream is a stack. So that stack is basically your work queue. That's where you're taking things off, and you need to process it in some way. So in this case, this is an example of streaming software. So streaming software is basically a way to connect different data sources together and send it to a location for analysis. So that's streaming, right? So that's streaming software. So you have continuous data, you have continuous data spouts. So you have raw data connected to a stream, and then that stream is basically piling up that set of papers, right? Okay. Okay. So now we need to put the data somewhere. So as I mentioned, you have this crazy stack of papers now, and now you need to process it in some way. So you need to put it somewhere. So it accumulates in something called a data lake. Like your raw data accumulates in a data lake. The data lake is where that's where you put all of your infrastructure. That's where you put all your data for analysis. So in this case, you can think of the data lake as just your table, your desk. That's where stuff accumulates. And then when you want to get work done, you take things off the desk and you start processing it. So a data lake is pretty typical. So the canonical data lake is HDFS, Hadoop file system. So Hadoop file system is basically a way to connect several computers together and so what you can do is view computers as just a pool of storage. So a data lake is very typical. You typically put raw data here. You can also do things like archiving here. So you can just take raw data, dump it in there, and you're set to go. So data scientists, many of you use this on a day-to-day basis. Maybe you're using it from Python or R or something like that, but at the end of the day, you're using some kind of a centralized storage. It used to be NFS, but at the end of the day, you just need one easy place to access the data managed by IT. So that ends up being called a data lake. So again, if we keep with this paper analogy, that is then just your desk, right? So now you have all these papers. So now you've analyzed all these things, right? Does that make sense? You're kind of analyzing these things. You're taking things off the stack. You're analyzing this data, and now what you want to do is you want to find the hackers, right? You want to find the bad activity. You want to sift through all these papers and find, oh, this is bad. I better do something about this. So you need to be able to find that. So that's kind of this idea of the needle in the haystack, right? So where are we here? Okay, so now what are we doing with these papers? It turns out these papers, in order to be processed, I need them to be cleaned. They're coming in wrinkled right now. They're coming in with messy handwriting. So what do I need to do? I need to pre-process that data in some way. So logs are typically very messy. They have different, in this case with different data sources, they have different formats that you need to think about. The dates, maybe the dates aren't all in the same format. Maybe there's different time zones, different teams. Different teams may manage these various data sources, right? So you need to take all this raw data in this data lake and pre-process it in some way. So if we stick with this paper analogy, that is then taking all these papers and straightening them up, right? So that's a typical data pipeline. So there's something called a data engineer at a company. A data engineer takes this data, pre-processes it in some way, cleans it up, and puts it out there for the data scientist to analyze. And then that's when you can jump into, that's finally when you can maybe get to Python. But what I want to get to, one thing I want to allude to here is that there's a lot of stuff that happens behind the scenes to actually build a complete product. This is where 80% of your time as a data scientist is spent, is in pre-processing your data. It's not actually in working on the cool machine learning algorithm. It's actually in data prep. So it's in straightening up that stack of papers. Because it turns out, any neural network, depending on how you represent the data, has a fixed length feature vector of some kind. And that fixed length feature vector is that's your standardized piece of paper that you can actually analyze, right? Because neural nets are dumb. They are dumb. They sound cool, but inherently, they're pattern recognition machines. They point at things. They find the bad behavior. They find what you tell them to. They recognize similarities. But they're not smart. They need a fixed structure to start with. So it turns out that this is true for all of machine learning and deep learning. You need a fixed representation of your data. So in this case, with these raw unstructured logs, you need to come up with a fixed representation that represents the activity on your network. And then you need to be able to feed that to a neural network in order to actually surface that bad behavior. So in this case, what you're typically doing is you start with your raw data, you have your stream, that stream sends it to a data lake, and then you run it through some sort of pre-processing, and then finally, then you get to the algorithm. That's when you get to the neural net. So I'll just give, briefly, an overview of what we do for deep learning. We use something called a variational autoencoder for identifying anomalies. So what we do is we use something called unsupervised learning, variational autoencoders that basically they basically do something called representation learning. What they do is how they learn is variational autoencoders look at two things. They look at the real data, and then they look at a reconstruction. And what they basically do is they have this reconstruction, and they basically they try to draw it, and then they compare them. How well did I draw that hand? Oh, it's not good yet. Okay, let me try again. And then eventually, so what you're doing is, what it eventually learns how to do is it learns its own good representation of the data. But it turns out with autoencoders, when you use its representation, it's actually very similar to a support vector machine, which is another algorithm that basically takes the data and reorients it. So what I mean by reorienting the data, I mean it separates it in a better way. So it kind of reprojects the data. So what I mean by a projection is a simple way of saying, I'm gonna turn this sideways. And it turns out I can look at the data better sideways than I can straight up and down, right? Like so what an autoencoder does is it's a very good representation of the data. It turns it sideways so I can actually look at it. And then actually, another thing autoencoders do, and why deep learning is very good at this, is you can also then stack them. So what I mean by stacking is you can compress the information. So it turns out that you then get a small feature vector that learns a compressed representation of the data. That is called representation learning. And so that representation, you can do clustering with it. You can also compute like a standard deviation of the reconstruction error. So reconstruction error is the similarity score between the real and the new output, right? Like so an anomaly has an abnormally high reconstruction error. It turns out you can actually use that to identify anomalies. And this is all completely unlabeled. So variational autoencoders, the reason we use those instead of just normal ones is they can basically approximate the data better. And so there's a lot of various representations of the data like that you want to do. So what we do is we then take that raw data, that fixed representation, and then we run it through an autoencoder, and the autoencoder learns its own representation. So in this case, what you end up with is terabytes of data, right? So you have terabytes of data in your data lake. You feed all that to an autoencoder, completely unlabeled, just as is, and it will be able to find the anomaly. So what you typically do is you take the data lake, you run a clustering algorithm on it, on that representation it learns, right? And from that is where you're going to get an understanding of the data itself. And it's based on the neural net's understanding of the world, not the raw data. The raw data is hard to learn from. The neural net's representation, it turns out, is actually highly robust to noise as well. So there's a lot of minor reasons for this, but basically once you get to your data lake, then you have the algorithm. Then you're actually identifying 0 or 1, right? 0 or 1. This yes or no. This is fraud. This is not fraud. This is an anomaly. This is a hacker. This is not a hacker. I'll just give you another example use case. One of our customers is Canonical, the company behind Ubuntu Linux. I'm sure you guys know what Ubuntu is. So we actually detected, we're actually able to do network intrusion as well as hardware infrastructure. So basically identifying broken servers. Same idea, right? Like so it was all based on this idea of a data lake. And so we use autoencoders for a lot of this. So we don't even really require labeled data at all. Just kind of nice, because it turns out anomaly, one of the problems with anomaly detection is it's always unbalanced. There's a lot of normal and very few anomalies. So in this case, it's really hard to do supervised learning when you're trying to do this. So if you use a variational autoencoder, not only do you get a better representation that's compressed that you can analyze, but it's able to automatically find the pattern, so you don't have to label the data. In this case, so one of the things we typically do is my competition is actually not machine learning algorithms. It's actually rules engines. So it turns out rules engines are still they're still the main way of, especially in Japan, they're actually still the main way of doing fraud detection or any kind of anomaly. It's actually based on raw rules. So your bank just has a bunch of hard-coded rules hidden somewhere, and they don't want you to know what they are. So why deep learning for this then? What you want to be able to do is you want to be able to identify new patterns. So it turns out the normal behavior always has a fixed pattern, and there should be no surprises. The neural net, what it's really good at doing is spotting these surprises. So it's able to adapt to new behavior. And so that's why a lot of people are evaluating machine intelligence now. So in this case, what we typically do then is part of this data pipeline is what we'll typically do is we'll also have a rules engine right alongside this as a new input. So what we do is we catch anomalies that the rules engine doesn't. And then the rules engine safeguards against, you have your old baseline. But human analysts will then be able to use both systems. And so that's typically what we see in production infrastructure today. All right, and finally we get to the exciting part. So I already mentioned the representation learning earlier, but this is now where we're connecting to the product. So this is where you're deploying to production. So in this case, you train your model, and now you want to use the model. You want to use it in production. So you usually have a REST API of some kind. You send a CSV, and you get back a score, yes or no. This is fraud. This is an anomaly, whatever. And then you visualize the outcomes. And that's finally when you get back to your product manager. Your product manager only sees that last part. They don't see everything else that goes on behind the scenes. Data scientists don't see this part, right? Like, so this is what a complete actual product looks like. This is what a complete pipeline looks like. Data scientists see one part. They only see like this part, and then your product manager sees this part. And this is typically your web development team that builds these kinds of dashboards and stuff. And so building an actual product, turns out, is very hard. It's not just, so you need to not only think about the infrastructure, you need to think about the problem. So just one small example of this, latency. So if I want to predict an anomaly, I want to do it if I want to be able to score every credit card swipe coming through, every hacker on the network or whatever, right? I need to do that within milliseconds, because otherwise, why is it useful? Right? Like you need to be able to do it within a certain time window. So that's why you need to think about this kind of infrastructure. So when you're doing deep learning, it turns out one other good application of it is it's good at scoring. It's actually very fast. So millisecond analysis of an individual example is actually very easy. So if you have your data pipeline attached to a neural net, it turns out you can actually get production grade anomaly detection. And it's actually practical. And so finally, I'll just kind of go over this real quick. So one of the things I want to talk about though is the representation. So feel free to read this if you want. But one of the things I want to cover up here is this idea of like, what is this representation? One of these things is one-hot encoding. So categorical data is something you're doing a lot of anomaly detection over. So if you're wondering what kind of data typically goes into a neural net for this, it's a lot of categorical data. So in this case, location data. Are they in a specific region or not? Is their name, what country are they in, right? It's a lot of, in this case, you have 26 countries you're targeting. You have a bunch of zeros and then one in there. So if they're in Japan, it's one, right? Like so that one-hot encoding is typically, that's a lot of what we're analyzing, especially when you're doing unstructured data like this. So you take data and you basically compress it down into this one-hot representation, and that's what the autoencoder then learns. Okay, so one of the things I just want to go into is a brief demo. So like, what does this actually look like? So I'm going to try to just go full screen here. Okay, so this is an example. This is an example anomaly detection solution from us. So what we're doing is we actually have a neural net that based on these probabilities can actually identify traffic in real time. So this country is hacking this country with this probability, right? And then you see the blue up there. The blue is actually the spotted anomalies. So you have a real-time dashboard with a neural network, and what it's doing is it's able to look at it's actually human inspectable. Like I can read this. I know where the anomalies are, and this is a real-time activity of the neural net actually identifying anomalies. So does this make sense? This is what you put at the end. This is the visualization you use, and then in this case, what you're doing here is this real-time stream. This real-time stream is coming from the neural network itself. So you're repeatedly sending web logs to it. You're running your data pipeline, and then you're extracting things. You're extracting things that you can use, like things that are human observable, and then you're attaching kind of the neural net's probability to that. So you use the neural net's probability with introspection from the original inputs. So one of the problems with deep learning is it's this black box, right? But it turns out if you can visualize it properly, you can benefit from the accuracy with having some sort of introspection. So when you're doing deep learning, if you want to deploy it in production, have something that audits the data. In this case, the buzzword for this is data governance. So data governance is tightly securing your data, watching it, seeing what the inputs are, and tracking what's going on. Track what goes into the neural net. And with that, you can actually deploy deep learning to production. And so, okay, so with that, I will take questions. Anything? Come on, people.
Thanks for the presentation. What is the data and input for this demo?
So web logs. So actual just raw web packets. So various kinds of traffic, such as the input, right? Like so TCP, UDP, location, IP, is it in this location or not, that kind of stuff.
Okay, and my second question, if I followed correctly, you are doing auto-encoding on the data that comes in on our network. And do you do a clustering after that? Or
Yeah, so.
すいません。
Oh, yeah.
Please repeat the question because
Sure.
interpreter cannot understand
sure.
the meaning.
So sorry about that. So the first one, the first question was, wait, okay, repeat your question so I can.
あるいはこちらのところへ来て質問していただけますでしょうか。どちら
Yeah,
でも
go ahead and the mic will be easier. Yeah, sorry about that.
Okay, thanks for the presentation.
Oop. All right, almost there.
Yeah, my first question was just to clarify what data was coming in.
Right.
This
Okay.
demo.
So what kind of data are we inputting into this? So raw web logs, right? Like so the IP, the location, in this case the type of traffic, that kind of stuff. And then second question.
Okay.
Yeah.
The second question that is more in depth is about the architecture of your network.
Okay.
So you have autoencoders at first that filter the data and do simplified representation.
Right.
Then, if I understand, this is where it's a bit more.
I
not
think
so clear for me, but how do you do the clustering part?
Right. Well, so what we actually do is basically the question is, how do we use an autoencoder for anomaly detection? And so what we actually do is we take the raw data, we fit it on all the data, and then basically what we learn is a representation. And then what we do is we actually track reconstruction error over time, and so we can do that in a streaming context. So in this case, we can do that in real time. So we track a standard deviation of the reconstruction error, and anything that's abnormally high for a contiguous amount of time is probably an anomaly. So think of it as a time series, and you have a spike. So when you have a spike in the anomaly, that's when we say, oh no, that's bad, right? And then that's what we surface. That's what we would surface on a dashboard like this, is that spike, and then we can do this automatically.
他に質問ございますか。はいどうぞ。
But then surely you need to know some way as to whether that spike, the forecast of your spike is true or not.
Well, right. So that's up to it. So the question is, then how do you know if it's true or not? So the whole point of using deep learning is to have some sort of human in the loop AI, right? Like so, all you want to do is you have human analysts already. So you want to make them more successful. So I pitched deep learning for anomaly detection as an assistant. It's an assisting tool. That's why I said earlier that we deploy alongside rules engines for that kind of stuff.
Okay, which leads on to my second question, which is, what are some of the challenges that you faced when you're trying to incorporate the human in the loop? Because surely that should also ultimately be one of the inputs into the model.
Well, so that usually happens. So the second question is, how do you incorporate the human? So what it turns out that they're actually all they want to do is they want to look at a dashboard and they want to click things. So if you can rank that stuff for them, that's all they want. So they're just clicking one by one. If you can do that, you're set. So all you got to do is you got to rank it for them. So you basically set their priority list, and that's what they're interested in, because they have billions of things to go through. So if you can make that 1 million instead of 1 billion, that's worth something.
他にはございますか。はい。
Thank you for your presentation. I want to ask about a little bit, because you mentioned about to learn using unsupervised to learn the representation. So could you explain a little bit more about that?
Sure. So basically, an autoencoder, what it does is, I think I mentioned this earlier. So basically, you have this idea of reconstruction error. So you learn, there's a loss function you can use called KL divergence, which is basically the similarity between two probability distributions. So an autoencoder, what it does is it looks at the input data as a distribution and the output as a distribution and compares the two. And what it does is it actually uses that and does gradient descent. And when it does gradient descent, that's when it learns how to reconstruct the original input. So the better that gets, the easier it is for it to detect an anomaly, and the better it is for it to use that representation for kind of like a compressed version of the original input. So that compressed version is what you're doing clustering or statistics on.
よろしいでしょうか。I have one question, but if someone is, どうぞ。時間もございますので、これで最後にさせていただければと思いますけど。
すみません。Thank you for the presentation. Earlier you mentioned that you are looking at, you input some weblogs, you encode them, you cluster them, and then you compare the anomaly based on the standard deviation.
Right.
So it seems that if they are spaced along the time, there will be a lower chance to pick them up. Are you looking at it also in another way to reflect the dispersion across time?
Yeah, so a lot of what we do is we mainly analyze short-range dependencies. In this case, like think about financial stock data. It turns out in practice, when you're doing financial analysis, the last 20 years doesn't matter. Only the last week does, right? Last week, last month. So we look at short-range dependencies and track that only. That's how we're able to adapt to new trends over time.
まだいろいろあるかと思いますけども、時間の関係もございますので、ここでの、Q&A は終わりにしたいと思います。大変貴重な、そして面白い発表いただきまして感謝いたします。Thank you for presenting your nice and great talk, Mr. Gibson. Thank you so much. どうもありがとうございました。